to introduce to you what sine, cosine, and tangent are.
Oh, I have to pay attention.
So, um, my thought is if you understand, obviously we take our calculator out, and you don't have to do this right now, but we are going to use Desmos. So if you don't have your computer open, you might want to open that up. But if I type in some things on my calculator like sine of 30 and sine of 23 and cosine of 14, where are those numbers coming from? What are those numbers? Okay, because I think a lot of times, maybe in algebra, maybe 8th grade math, when you may have used this stuff before, you're just told to use those buttons, but never really explain to what those numbers are and where they're coming from, and maybe even how your computer or your calculator knows to spit those numbers back to you, of like, sine of 30 is 0.5. How does the calculator know that? So that might be something we talk about, understanding how the calculator is working, maybe later next week. But right now, I want you to have an understanding of what sine, cosine, and tangent are. And they're just names for particular ratios. Okay? But we got to decide what those ratios are, determine what those ratios are. So, in doing that, I'm going to look at these two triangles. Okay? And these two triangles, because I'm using arbitrary values for their side lengths, represent any right triangle that you could ever create. Okay? And what do you know about those two triangles based on how I've got them set up to one another? They're both right triangles. What do we know from chapter 7? They're similar, okay? They both have a right angle, and they're both sharing this angle down here, right? Okay? So we know that they're similar by angle. Now, I'm going to call, and it's just for right now just for a referencing purpose, I'm going to call this angle right here that. Does anybody know what that is? What that symbol is? It's a Greek letter. Say it again. What'd you say? You said something.
He said beta.
You said beta? You're really close.
Alpha. Sigma.
It's called theta. Okay? We will see alpha at some point. Might be a good idea to write these down. I don't know. That's alpha. Maybe you've seen that somewhere else. Okay, that's beta. Yes. Okay. You would see these in fraternities. Okay, that's the Greek alphabet. Pi is a Greek letter. Okay, you've already seen that one. But those are usually what we use theta, alpha, and beta a lot of times, even omega and gamma, to determine angles or to talk about angles, to label it. Instead of calling it like angle A or angle 1 or something like that, just the trigonometry. School of thought or community says we're going to use those symbols. Okay. If these two triangles are similar, okay, so I'm going to call this triangle up here, I'm going to call these parts, let's call that Y, call that X, I'll call that Z. Because these two triangles are similar, would you guys agree that we could write a couple proportions here? We could write Y. What would Y compare to from the okay, you should go to A, so Y to A. What should Z compare to? C. And what should X compare to? B. Okay. Now you can put those in any order, but they're all equal, right? That's what we talked about in chapter 7. What I want you to understand is chapter 8 is simply kind of fallout or a byproduct of what we've already discussed in another chapter. Okay? We knew that in chapter 7, if these three things were true, we could take maybe those two and say that is a true proportion, right? So I'm going to write down that Y over A is equal to Z over C. Okay? And if I look at this, that's comparing part of triangle, we'll call this triangle number 1 and triangle number 2. It's comparing part of triangle 1 to a part of triangle 2, right? We knew from last chapter that those two things can be interchanged, right? We are allowed to interchange the means. So if I take that set of means and flip-flop them, I get that proportion. Okay, I'm just going to be able to call them the blue proportion, the red proportion. But if I look at the blue proportion, like I said, that's now comparing a part from triangle 1 to a part from triangle 2. So you jump from one triangle to the next. If I interchange the means, which produces still true proportions, now look at y compared to z. Where did those components come from? Y and z both come from triangle 1. And A and C both come from triangle number 2. So now what we're saying here is that we can now compare, because using what we talked about in chapter 7, we can now compare, instead of jumping from one triangle to another or one figure to another, we can stay inside one triangle and just compare the parts of that one triangle to one another. And we should still get true proportions. Now, the fact is, okay, this y and z and this a and c, they can be anything they want to be as long as these angles theta are the same thing, because then they have to be similar triangles. If this angle here was, I don't know, 30 degrees, and this angle here was 20 degrees, these relationships don't exist, okay? These would have to both be 30 degrees or both be 20 degrees or something like that. What we're saying is, if that theta is the same, and this is a right triangle and this is a right triangle here, that any triangle with that angle measurement, okay, any right triangle with that angle measurement, okay, is going to have what we call the opposite side divided by the hypotenuse. That quotient is going to be the same regardless of the triangle, okay, as long as it has a right angle in this angle theta, okay. What I mean by that, let's go back to what we did. Well, let's call this. We have a definition for this. We have a name that we can apply to this ratio when we say opposite divided by hypotenuse. Does anybody remember from a previous course what opposite divided by hypotenuse is? Starts with an S. Sine. Okay? This is called the sine ratio. And all it means is that you're taking the opposite side of the angle that you are dealing with. Okay? So I'm going to know that angle. I take the opposite side and I divide it by the hypotenuse. So it's a sine ratio, and this is the way we'll algebraically deal with it. We'll say the sine of theta. So when I write it that way, theta is the angle that I reference, that I'm paying attention to. And I look, okay, what is the side opposite that? And what is the side that is the hypotenuse? And I'll divide those two things, and that's what will equate then to the sine of that whatever. Maybe whatever that measurement is, okay? Well, I'm going to show you, because eventually then, we're going to take one of these values away, okay? And I'll ask you to find the missing one based off of knowing just maybe the hypotenuse or just knowing this. So I'll get to that. It's a good question, but let's go a little bit further with this real quick. What we know from maybe the last section, okay? Let's say that I have a couple 30, 60, 90 triangles here. All right. So let's say that's a 30, 60, 90 triangle. Let's put 30 degrees right here. 90 would be there. 60 would be there. Let's say that I just arbitrarily chose a number, this to be 5. Okay? What's your hypotenuse going to be? 10. Okay? And this would be 5 radical 3, right? Not really worried about the radical 3 part right now, but that would be true. So let's just write that in red. If I took another triangle, that was a 30, 60, 90. Okay, but maybe I alter the size. So let's just, to prove that point, make it that triangle. Let's still say that this is 30 degrees there. Okay, let's say this distance here is 2. What would the hypotenuse be? 4. And now this side down here would be 2 radical 3, right? And we'll just do one more. We knew that every single time that we had it, and we proved this, every single time we had a 30-degree angle, across from it was n, this was 2n, and this was n radical 3, right? Okay. I want to go back through each one of these, and I want you to look at the 30 degrees. I want you to tell me what is the opposite side of 30. 5. What do you get for the hypotenuse? 10. And if you do 5 divided by 10, you get 1 over 2. Come to this one. Opposite side of 30, 2 over 4. 1 over 2. Okay, look at this one. Opposite side of 30. Hypotenuse is 2n. So those n's cancel out and leaves me 1 over 2. Okay, so what we're seeing here, hopefully you see, with just a few examples and then the general case, that when I ask what the sine of 30 is, I'm actually asking what is the opposite side of the right triangle divided by hypotenuse if that right triangle has a 30-degree angle. You should always get 1/2 back. Okay? Take your calculator out. I want you guys to go to Desmos.com. Desmos.com. I want you to have that calculator open and running, and I want you to type in actually, before we type anything in, come up to this wrench up here and go down to where it says degrees, and just make sure degrees is highlighted green. All right, and then come over here into the column that you can use your calculator and just type in sine, parenthesis 30, and what's it spit back? 0.5. It's spit back the same exact 1/2 that we found in all those examples, right? Okay. So your calculator knows, and I'll explain to you later on why it knows this or how it's pulling this number out. But it knows that every single right triangle that we deal with that has a 30-degree angle, the quotient of the opposite of that 30 degrees and the hypotenuse is going to be 1/2. Throughout the day, we kind of constructed this. Okay. If we look at, let's see here, that distance, okay, and let's hide that. All right, so right now I'm going to change this angle to 30 degrees, okay? So I've got a right triangle here, correct? Okay, it's saying that this side here is, I'm calling it K, which is 2.7. I is the hypotenuse, 5.514. And what I want you guys to recognize now, you could argue, well, you just put 1/2 up here. If I go to this number right here, see how that equation says K divided by I? Okay, so it's just pulling out whatever this K was. So it's changing all the time. And it's kind of mimicked up here. If I start to, if I just do that division with those two numbers, I get 1/2. If I take and change those numbers, see how those numbers change? Does the 1/2 ever change? No. Okay. And even over here with the K divided by I, okay. And if you were to, now I'd have to do this with a little bit better rounding, but if I did that, if you took those two numbers on your calculator, typed them in, you're gonna get like 0.499999999 back, which because of rounding, we could assume is 0.5. Does that make sense, everyone? Okay. And all of these triangles are representing, because I can make I and K essentially anything, right? Okay. It's representing all the infinite triangles that have a 30-degree angle in it. Okay, and I look opposite and hypotenuse. The quotient of those is always 1/2. Okay, now your calculator also knows that when you have a 29-degree angle, the quotient of those two things is 0.4848. Is that okay with everybody? And that 0.4848 is that number divided by that number. Okay? Go to Desmos and type in sine of 29, and you see that it's spitting back that 0.4848 number, right?
4848093.
Right. So what I want to show you, what I want you to understand, is that these numbers are not, I think they're in Algebra 1 or 8th grade math, you were told, just use sine 29. You hit enter, it gives you this long decimal, and it's like magic that number shows up. You have no idea where that number comes from. It is coming from the idea that we have similar triangles, and that no matter what, when you have a triangle that has a 29-degree angle in it, if you look opposite that and hypotenuse of that, and you divide them in that order, you're going to get that ratio right there. Okay? Which we're going to view that ratio kind of as a scale factor. Okay? Because we're going to use that to find missing parts of our triangle. Okay? Now this only works in right triangles right now. Okay? Or at least this simplified version of using sine, cosine, tangent. We have some theorems that allow us to create some formulas that incorporate sine, cosine, tangent. They're a little bit more complicated that allow us to work inside all triangles. But right now we're going to focus just on right triangles. Okay. So you guys remember when we did 30, 60, 90 triangles. Okay. Here's the thing: 30, 60, 90 triangles. If this was 30 degrees, we knew that this was in, this was 2n, and this was in radical 3, right? Okay. Well, right now, let me just put in, let's just go 20 right here. I just want to see what he evaluates to be 20. If I had a 20-degree angle in here, we could have a template that says this is, so I'm going to go, and this would be n, and this would be 0.34 n, is that right? No. This would be, we could write this as 0.34 n, and this would be n. Does that kind of make sense? Okay, because now I could have a template for a 20-degree angle, okay? But this 0.34 is a much uglier number than what 1 and 2 were, right? And then every other angle measurement would have, 20 has that template. 21 would have a different one. 23 would have a different one. Does that make sense? We only learn the 30, 60, 90, the 45, 45, 90, because those are the ones that are most common to us. They show up a lot. They're very useful to us. It might be rare that I see a 20-degree angle in a triangle. For the same reason, 20.2345 is going to be another angle, and it gives me another ratio of side lengths being divided by 100. Okay? Does that kind of make sense? So these ratios are simply taking the quotient of sides of the triangle. Okay? It's got to be in a right triangle. That being said, let's deal with a question. Okay, let's make this a 52-degree angle. Well, I think before that, let's go to 60 degree. Because 60 degrees, okay, think about looking at a 60-degree angle using special right triangles, okay? Here's 30, here's 60, okay? If I go in, 2n, in radical 3 here. Now I use sine of 60, so I'm looking at that 60. Go opposite, which would be my numerator, and then hypotenuse would be 2n. What's that cancel out to give me? The ends drop out, gives me radical 3 over 2, right? So whenever I have a sine of 60 degrees, I'm going to get radical 3 over 2, which type that on your calculator, it's 0.866. Okay. Let's kind of work with it and see how this benefits us. Like I said, we'll go to 52-degree angle here. Let's say, just to make it easy, right now, let's say we don't know that value. And just for calculating purposes, let's just round that to 3 decimal places. Let's say you're looking for x. Looking for that distance right there. Okay? Would you guys make the argument that that is the opposite side in regards to this angle down here, alpha? Okay? Would you agree that this is the hypotenuse? Does that make sense, everyone? Okay? If that's a 52-degree angle, okay? Our calculator, I think I got that one right, was BD divided by BC. BD. No, that's wrong. What's this one? Our calculator knows that when you have a 52-degree angle, the opposite side divided by hypotenuse should always equate to 0.788. Okay? And if you type it on your calculator, you see that as well. So if I type in sine of 52, 0.788, okay? So that means essentially, guys, that one of these side lengths, it's the hypotenuse. Let's say it this way. X is essentially 78% the size of the hypotenuse. Does that make sense? Okay? There's a ratio here that's going to allow me to shrink the hypotenuse so that it becomes the opposite side. That's all these trig ratios are doing for us. Okay? Because we know that if I have those parts, opposite and hypotenuse, the sine of 52 is equal to the opposite side, which we're calling x right now, divided by the hypotenuse, and that's 9.655. Okay? So it's telling me what, now sine of 52, remember that's 0.788. It's saying whatever x is, right, divided by 9.655, I know that that's going to equate to 0.788. Okay? So think about this. If I gave you a numerator of x in a denominator of 4, right, I told you that's going to equate to a half. Don't you know what the numerator has to be? Don't you know that the numerator has to be 2? I gave you x to be my numerator, denominator to be 4. Right, I tell you that that fraction is going to equate to a half. You know what that numerator should be. So it's the same idea. Okay? I don't know this numerator. I know my denominator. I'm going to divide my number by something, some unknown value by 9.6555. Okay? But I know that that should equate, whatever that is, it should equate to 0.788, which is the sine of 52. Okay? So if I write it this way, think about this. How do I find that information? Kind of like how I would have said if x is over 4, is this going to equal 1/2? Don't I multiply both sides by 4 to get my 2? Okay? So what would I multiply both sides here by to get x? Yeah, I'm going to multiply by that denominator. So I multiply by 9.655, and I come over here, 9.655 times 0.788, and that should equal x. Okay, now here's the only issue, the way I've written this. We never want to write sine of 52 as 0.788 because I had to round it. Does that make sense? Sine of 52, usually with these things, they're probably irrational numbers. Okay, these decimals. If I go, let's just see. I think one of those is actually right here. Okay, so that's that number right there. And that's only out to like 10 or 15 decimal places. It keeps going on, and you don't see a pattern there, do you? So most likely it's an irrational number. So I don't want to cut that off at that second 8. I don't want to cut it off at 0, 1. I don't want to cut it off at 753. I want the whole thing. Okay? So instead of cutting it off, what we do is we use, especially with the irrational numbers, this is what we're going to do all the time. We never want to use the value. We want to use the symbol that represents that number. So that's a symbol that represents another number, much like radical 2 represented another number like 1.414 something, right? Does that make sense? But I don't want to use that one because I rounded it. I have to stop at some point. So we use that one in our algebra. Same thing here. We're going to use that one. And what's nice about using that one is that our calculator is programmed out to enough decimal places. It doesn't use infinite, but it uses enough to where we can get a really, 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 really accurate answer. Okay? So what we're going to do is we'll type in 9 point. What was it? 9.6. Was it 5.5? Yeah. And then sine of 52. And that should be then the length of that side that we're looking for. That should be x. 7.6. Is that okay? Now I'm going to go to GeoGebra and see if, because GeoGebra is going to do it differently. GeoGebra is going to do the distance formula with those 2 points. It's going to do y2 minus y1 over x2 minus x1. Or sorry, no, it's not. It's going to do the square root of x2 minus x1 squared plus y sub 2 minus y sub 1 squared, right? That's our distance formula. And if we ask it to do that, 7.608. And that's exactly what we found using this formula here, this equation. Okay? So, when we deal with you guys have maybe referred to this as SOHCAHTOA in the past, right? You heard that phrase? Okay? We'll spend more time on that tomorrow. Yep. What I want you to understand, everything that we deal with right now with SOHCAHTOA is because those two triangles are similar. If theta is the same angle measurement in both of them, okay? That means then that every single triangle that has a 51-degree angle in it is going to have the opposite side divided by the hypotenuse to be the same quotient. Every triangle, right triangle that has a 27.24-degree angle in it is going to have the same opposite divided by hypotenuse quotient. Okay? Is that doable? Does that make sense? So that is only one of the 3 ratios. The other 3, and I think we might have a little bit of time here to talk at least about these 2. Okay? If I look at those 2, we got z over c and x over b. If I interchange those, I get z over x and c over b. We don't usually like to compare it that way. We like to look at the reciprocal. So I'm going to take x over z and b over c. And that's because we always like the hypotenuse to be on the bottom. Okay? And that then becomes, if I look at the triangles over here, comparing x to z, we'll finish this tomorrow. No new homework.